Okay, Assalamualaikum all. I'm going to just review or give you the summary of the experiments what we did. Okay, so let me start with tubular reactor. Okay, so first of all, tubular reactor, what you did, you prepared a solution of NaOH and ethyl acetate, right? You put this in feed tank. So whatever the concentration is of NaOH, whatever concentration of ethyl acetate, you pump this and it is mixing in the reactor in the entrance of the reactor. So if it's tubular, this goes to tube. Okay, so using the mole balance, you should be able to find the concentration of A and B. A is NaOH, B is ethyl acetate. So same concept in Cstr as well. So Ca0, Cb0, simple mole balance. So this, first of all, you find this one. Okay, based on the what you have at the inlet of the reactor, you will find the lambda 0 connectivity of uh, at initial at zero conversion or initial connectivity. Okay, so that's lambda 0, and you need lambda infinity. Lambda infinity is assuming 100% conversion. So this one either should be given or you have to calculate based on what you have in the beginning. So suppose A plus B giving you C plus D, and you have 0.1 molar, 0.1 molar. This is Ca0, Cb0. Okay, Ca0, Cb0. Initial concentration after mixing. Okay, so at 100% conversion, you will have this one 0, this one 0. Sodium acetate 0.1, ethanol 0.1. So 100% conversion will be of this doesn't have anything. So you have 0.1 molar sodium acetate. Ethanol doesn't have any connectivity. So in this case, lambda infinity will be connectivity of 0.1 molar sodium acetate. And you have the correlation of sodium acetate with concentration and temperature. You can put it, you get the lambda infinity. So lambda infinity, lambda 0. Okay, so for example, if A and B, if they are not equimolar, okay, what happens? Suppose NaOH is 0.2, ethyl acetate is 0.1. Now you want to find lambda infinity. When we say 100% conversion, it means that 100% conversion of limiting reactant. Okay, so limiting reactant in this case is B. So this will consume 100%. So this will goes to 0. So 0.1 molar B all consumed. So this will also react 0.1, 1 to 1, right? So this you will have left over 0.1 molar NaOH A, and then sodium acetate 1 to 1, again 0.1 molar. D also 0.1 molar. D is ethanol, no connectivity. This one is 0. So now lambda infinity is will be the connectivity at 100% conversion. So what you have? You have 0.1 molar sodium acetate and leftover 0.1 molar NaOH. So in this case, lambda infinity will be lambda of 0.1 molar NaOH plus lambda of 0.1 molar sodium acetate. Okay, so this is the way to find lambda infinity if they are not in equimolar condition. So once you know the lambda infinity, lambda 0, you can get the conversion. Ca by Ca naught is lambda minus lambda infinity, lambda 0 minus lambda infinity, right? Lambda 0 is known, lambda infinity, lambda is the measured in the reactor, or for plug flow it is at the exit of the reactor. So using this you can find the conversion. Okay, so what you did, you find the rate constant. So rate constant for, so design equation for plug flow reactor when Ca0 is Cb0 is this, right? So you know the conversion, you know the residence time, volume of the reactor divided by feed flow rate. Ca0 is known, you can find the K, isn't it? So what you did, you studied at different flow rate or different time constant, different residence time, and even you have plotted K versus tau. K is function of temperature only, so a little bit of scattering, but ideally it should stay constant with some deviation. Okay, and also you studied the effect of residence time on conversion, right? So conversion versus residence time, you got something like this. It looks linear but it's not linear. Okay, so if you fit, it's like this. So now we know this equation, k tau C a naught equal to xa divided by 1 minus xa. Okay, so if you rearrange you will get this like this, xa, I'm trying to get conversion versus residence time. Okay, so now you can see that xa and tau is not linear. Okay, it's not linear. So when we say linear or proportional, it means that if we double the residence time, conversion should be double. But it is not like this. This is the equation. Suppose, let's see, suppose we have 30% conversion, okay, at given residence time or at a particular residence time tau. C a naught K is constant. So when 30% conversion, what you will have, your value of K tau C a naught will be xa 1 minus xa, right? So 30% conversion means 30 divided by 1 minus 0.3, 1 minus 0.3, right? So k tau C naught is 0.3 divided by 0.7. Okay, so this value is how much? Around, okay, let me calculate. 0.3 divided by 0.7. Okay, 0.42343. So at this condition means this is the value of k tau C a naught. If we double the suppositions time, what will be the conversion? So if we double the conversion time, keeping the constant same temperature, same initial condition, so k remains same. If tau is double, what will happen? Your value of k tau C naught will be double. So you get 2 divided by times 0.43, which is 0.84. Okay. Now, if tau is double, we want to see what will be the conversion. So again, now we know this equation, k tau C a naught divided by 1 plus. So this is basically 0.84 divided by 1 plus 0. So which means that 0.84 divided by 1 point 0.45 conversion. So when 30 It was 30 before. Now the new conversion is 45%. So it's not doubling. It is less than this. Okay. So it is not double. So it is not linear. It's not proportional. So conversion also it will go. It will not go to more than 100. So 1 maximum. Fractional conversion 1. It will be like this. Okay. So initially it could be linear if you study this relation k tau ca naught 1 plus k tau ca naught. So what is happening at low, when tau is low, what will happen? This value will be low. So we can neglect with respect to 1. So that is become k tau ca naught. So at low conversion, you can expect that conversion will be proportional to tau. Okay. When conversion tau is very high, what happens? Very high. This value will be high as compared to 1. So in that case, conversion becomes k tau ca naught divided by this is negligible. 1 is negligible. So k tau ca naught. So conversion become close to 1. Yeah, that makes sense. Okay. So this is all about tubular reactor. Same we had Cstr. Cstr equation is this. So getting conversion and those are same. And if you plug this is second order equation. Second order equation means you will get this. So Cstr is difference differ in this sense. So this will be we have a square. In plug flow we don't have this square here. Okay. So conversion you can get the rate constant, or if all these known using then you can get the xa. K tau C naught is known, you can get the conversion at a particular feed condition or temperature. Okay. Now we study the dynamics, isn't it? Dynamics of Cstr. What we did, we run the reactor at particular flow rate. So tau is known at particular temperature, K is known, Ca naught is known. So what happens? So at a particular feed condition, we can get the conversion using this. So conversion is known. That's a steady state conversion. Conversion we know. Then concentration also we know now. That's the concentration. Now, if we change the feed flow rate is changed, what will happen? Tau will change. Tau will change, isn't it? Tau will change. If you change tau, it means that k tau C naught value will change. So again, using new value of k tau C naught, xa divided by 1 minus xa square, you can find the new xa and then new ca. Okay. So initially, so if you want to just draw what you did using MATLAB, ca versus time. So initially, suppose this was here, first at one steady state. Now we change the flow rate. Suppose we decrease the flow rate. If we decrease the flow rate, residence time will increase. So conversion will be more. Concentration of the reactant will decrease with time. So you will have something like this. So this is the new CA, new steady state. This is the old steady state. So you can draw with this known values. Okay. So this is and if you increase it will be otherwise. So this is an unsteady state temperature concentration profile for plug for Cstr. Okay. What else we have in Cstr? I think that's it. And then virtual experiment process dynamics. Okay, Cstr in series, dynamics of Cstr in series. So what you have, there is no reaction, only salt is moving, right? Salt is moving through the system. So we change the salt concentration, input salt concentration. This is C0 coming. So leaving C1, C2, C3. Yeah, mole balance is there. Your manual, you can have a look. So if we run a certain concentration of KCl, 0.1 molar, after some time in each CSTR, each tank concentration will be same. It will reach the 0.1, isn't it? 0.1. Now, if we give a step change to the input to CSTR, so from 0.1 to 0.15, suppose. So what will happen? Tank 1 will go to 0.15, typical first order. Tank 2 will receive from here and it will be like this. Tank 3 will have more delay because it will take from C2, from tank 2. This one easy, you know. Okay. Same thing we did for pulse input. Pulse input, what we assume? We assume that someone put the salt in tank 1. Okay, tank 1, 10 gram. Initial concentration was 0.1. So now the new concentration in the tank will be 0.1 plus 10 divided by the molecular weight of KCl divided by the volume of the reactor. That's new molarity adding to the tank 1. So that will be the, and suppose 0.1 molar NaKCl is running. So what you had, you 0.1 for all, but now tank 1 will jump. So initial concentration in tank 1 will be suppose 0.195, something like this. So it will jump, but it's one time. This addition was one time. It will jump, then start decreasing, and it will follow the same concentration, this one. So it will jump and then it will go to this. Tank 2 will get higher concentration from tank 1. Okay, and this will go increase and then again it will go to this. Tank 3 will also receive from tank 2 the higher concentration, increase, and then finally goes to previous steady state. Okay, so this is pulse input. So initial condition at t equal to 0, and final condition at t equal to infinity. We also did ask you to find the analytical exact solution for tank 1. For suppose you have something like this 1 for tank 1. If you want to know what is the initial concentration in tank 1, put t equal to 0. T equal to 0. So C is C0. And final conductivity, final concentration, steady state, T infinity, e power minus infinity is 0. C is 0. Okay. So this was about plug flow reactor and CSTR and virtual experiment. Okay. For RO, I have given you the summary already. It should be the same: finding the salt rejection, finding the recovery, which affects what. So as you know that increasing pressure increases the recovery and the salt rejection. Increasing temperature increases the recovery, but salt rejection decreases, right? Salinity, if you have feed concentration, if you increase the feed concentration, you have more osmotic pressure. So permeate flow rate will be less. So recovery will be less. Also the salt rejection will be less because you have more salt in feed. So increasing the feed also increases the decreases the salt rejection. Okay, I don't want to make it very long. That's it. Hope it will help you. Thank you.